everybody, and welcome to my NGSS activity, the egg drop. I found this on the NGSS website, but it was actually an online application, like a simulator, but I kind of wanted to do something hands-on. If I were to do this in the classroom, I think I wouldn't have the students do individual trials. We would all just do it collectively, and I would call up people to come help me demonstrate things, like dropping the eggs. So I have a handout that's in front of you that I'm going to start reading. Today we will be testing the limits of an eggshell. This activity will get you accustomed to the changes in momentum and the forces associated with them. Momentum is a vector quantity associated with movement that is the product of the object's velocity and mass. The equation for momentum is P is equal to mv. So the first thing I want to point out is that momentum is a vector quantity, so it has magnitude and direction. It is not a scalar quantity. Velocity also is a vector quantity. Mass is a scalar quantity. You can see it doesn't have a little arrow above it. Now, this wouldn't be like the students would be familiar with momentum. It wouldn't be like the first day. But momentum is kind of a difficult topic because the word's kind of like tossed around in everyday language, and people have a hard time understanding that momentum is like its own quantity. People like, oh, how it relates to energy and it relates to velocity, but you use it in its own right because it's very useful to talk about momentum. So that is the equation for momentum. Today we're going to assume that all of the eggs have equal mass. So pretty much you could just use the words like velocity and momentum interchangeably today, but that's really only for today. Usually it's the product of mass and velocity, but today it's all the masses are the same, so it's kind of just like velocity. So wherever you see a P, you could kind of replace it in your mind with a V, with velocity. So continuing. When the object is moving faster, its momentum increases. Impulse is a measure of the change in momentum. The force impulse equation is given by F is equal to, that triangle is called a delta, delta P over delta T. F is force. The students should be familiar with this quantity already from learning Newton's laws. Delta P is called impulse. People also use J, but I think it's more useful to include del P. And T is just time. Now, what's super important for this equation is it is describing collisions. The force is the force acting on the object. Delta P is the change in the object's momentum during the collision, and T is the time for the collision to take, how long the collision takes place, how long are those objects touching. So I'll continue reading. Here, F is force, P is momentum, and T is time. The triangle can be read as the change in. This equation states that the change in momentum divided by the change in time equals the force applied to the object over the time interval. That's exactly what I just said. To help understand the implications of this equation, I would like to make a sports analogy. Imagine, everyone close your eyes, and try to imagine a baseball player catching a fastball barehanded. They usually use gloves because this would hurt otherwise. But what motion do baseball players make when they're catching a ball barehanded? I'll display a video right now. An experienced player will kind of cradle the ball down with them and move their arms down as they're catching the ball, rather than just letting the ball clap into their hand really rapidly. If you kind of move your hands with the motion of the ball, it really softens the blow and you feel lesser force, and your hands wouldn't hurt as much. So continuing reading, by moving their hands back, they are giving the ball more time to slow down, making the denominator of the right-hand side larger. So the equation we were just talking about was a fraction. Delta T was on the bottom. Dividing by a bigger number is going to make the force smaller, causing the force to be less, resulting in less pain for the player. I want you to remember that analogy. Very useful for today. So today we will be exploring a similar situation, but with eggshells. We will drop the eggs from varying heights onto varying surfaces to see which situations break the egg. These next three sentences are very important. The egg breaking or not is determined by the magnitude of the force applied to it. So if F, in that equation we are talking about today, the impulse force equation, if F is really big, the egg's going to break. If F is really small, the egg is not going to break. The impulse, remember the impulse is the change in momentum. The impulse will be affected by the egg's velocity when changing initial heights. So I'm going to drop it from like knee height, belly button height, and then like above my head. Use the numbers the approximations 2 feet, 4 feet, and 10 feet. So when I drop the egg from a greater initial height, when it gets to the floor, it's going to have a greater velocity. And then the equation, the force impulse equation, describes collisions. So the change in momentum after the collision, after the egg hits the floor, the velocity is going to be 0. So it goes from moving really fast to not moving at all, which is a big change in impulse if it's dropped from a large height. The time of impact will be affected by how malleable or soft the surface is. So this is really associated with delta t, how soft the surface that it's falling on. Kind of like the baseball player, when he moves his hands down, he increases the time of impact, lessening the force on him, giving him less pain. So that's really important. We're going to have like rigid surfaces, and then we're going to have soft surfaces. So then I have a chart on the following side that I'll show you right now. So the following side is where the data collection is going to be taking place. I'm doing 9 different trials, 3 different heights of 2 feet, 4 feet, and 10 feet, and 3 different surfaces. I'm doing this on my deck outside, so it's like pretty much like a hard floor. And then I'm using a thin newspaper, so it's pretty much just a hard floor. A folded bed sheet. I folded a couple times, so it's a little thick, and a bowl of uncooked oatmeal. So I would ask the students to fill in the chart which situations do they think the egg will break and why do they think so. You guys could just do so right before you're watching the video, before I drop it, make your predictions. And then I also asked the students to mark down which times the egg broke and whether it was violently broke or if it broke lightly, and then some reasoning why they think it broke. Then I have some follow-up discussion questions that I'll go over after I show you the short clip of me doing the trials. And then I also have a little bonus clip where my mom and my sister hold up a bed sheet, and they're not holding it so that it's taut. It has a little bit of slack, and I throw the egg at it, and I ramp up the speed every single time. But first, here's me doing the trials, and I hope you guys like it because it took me a while to clean up. Okay, so here I am outside testing, dropping the eggs on the 3 different surfaces, the thin newspaper, the folded sheet, and a bowl of uncooked oatmeal. And I'm going to drop them from varying heights, and we're going to see when they break. So first I'll just do it from my knees on the newspaper. And it broke. You'll just have to take my word for it. Okay. Now for the bed sheet, I probably folded it like 8 times from my knees. Didn't break. Okay. Now the oatmeal also didn't break. Cool. So it only broke on the newspaper from knee height. Now I'm going to drop it from my belly button on the newspaper. Let's see if it breaks. Cracked in half, quite violently. God, this is disgusting. Okay. From the belly button onto the bed sheet. Didn't break. Now onto the oatmeal. Didn't break. All right. Now I'm going to stand on this here chair and do it from above my head. And let's see which ones break. Try and guess which one is going to break before I do it. Okay, I'm standing on the chair and I'm going to hold the egg above my head. This is probably like 10 feet more. All right, let's hope I have good aim. Absolutely splattered on the newspaper. I'm not even going to clean it up. It's such a mess. God, we're going to need the hose after this one. Okay. onto the bed sheet. It broke. Not so violently, so I can pick it up. All right, now for the oatmeal. From above my head into a bowl of uncooked oatmeal. Make your predictions. Oh, it hit the rim. It hit the rim. That doesn't count. That doesn't count. We're redoing it. We need a do-over. Oh my god, I suck. It didn't break. From above my head.
Just leave the egg in the
10 feet into the air, into a bowl of oatmeal. Did not break. Come pause the video. I'm gonna throw it harder every time. So I'm gonna like come and get it this time. Make sure you hold that tight. You're gonna drop that. You don't have a good grip on that. I want all your fingers on it. There you go. Alright, I'm gonna throw this as hard as I can.
Wow.
Alright, one more. Oh. No. You want to try it? Okay, I hope you guys enjoyed that fun little clip. I definitely had fun doing it. Now for the follow-up discussions, I think I would just ask the students like to pick a question and tell me the answer, like whichever one they want to answer, because I threw a bunch of them in there and they probably wouldn't know every single answer, but I would want them to participate. So I'll rattle off answers really quickly. This is taking too long. Which outcome surprised you the most? Personally, for me, it breaking on the bed sheet from 10 feet. I didn't think that was going to happen. When was the egg broken the most? When it was dropped really high, it broke the most, and when it was on the rigid surface, it broke the most. Why do you think that? The force impulse equation. When the egg didn't break, did you notice anything about the catching object? Yeah, it kind of like absorbs the blow. Like the bed sheet, if you look at it, it like cradles the egg on the way down. Unlike the newspaper, it's just rigid and doesn't even move. How is this like the baseball player example? It's softening the blow, increasing the time of the collision, lessening the force. Can you think of more safe surfaces? Grass. I wonder if rubber would be good. I know it would bounce. I don't know. A pillow, a mattress. What would happen if I threw the egg down instead of dropping it from rest? It would have a greater velocity when it reaches the ground, so it would be more likely to break. Why are newer cars safer with a crumple zone in the front hood compared to older, more rigid body models? Because it increases the time of the collision when the hood of the car where the engine is able to crumple and compress like a spring. It absorbs the blow, so it protects the driver more. Thank you guys. I hope you enjoyed it.